All right, we're in 9.3, so we're going to cover 9.3. We're not going to cover 9.4. 9.4, we're talking more about that in 202. We're talking about lattice energy, but we are definitely going to cover 9.3. So it shouldn't be a bad lecture today. All right, so we talk about enthalpy. And we were introduced to enthalpy in the lab that we're working on. So. We'll talk about the first law of thermodynamics, some enthalpy classifications, writing enthalpy equations or thermochemical equations, and then discuss Hess's law as well. So thermochemistry, right? This is a relationship between heat, work, and other forms of energy, right? When we talk about enthalpy, right? So substances can act as kind of like a reservoir. You know, with a reservoir, it'll collect water as it rains, so we can either add water to it, and we can also extract water from it, right? So energy is stored in substances, and we can use that as some kind of kinetic energy there. So there's a potential energy sitting there, and as we use those substances, we can collect that kinetic energy. So I mentioned also in a previous discussion where we talked about the system and its surroundings. So our system is the chemical reaction, right? If I write a chemical reaction, hydrogen plus oxygen, and we are going to get some liquid water out of that. Let's balance this. So this is considered to be the system, right? And for the system here, right, is that we're going to, this is an exothermic reaction. These are in the gas phase here. So we have 3 moles of gas molecules. We get 2 moles of water from that. But it is going from gas to liquid, and this is an exothermic process that heat is being released here. So this is producing heat. And we know heat, right, in this reaction, heat is leaving the system, right? And that's our Q. Q represents heat, right? It's not a unit, but this is what's going to represent heat. So we see heat leaving. We've also had reactions where we saw heat entering the system. We can see that here. So heat entering the system. Now, we're also going to introduce this W here, right? This W just represents work. So either the reaction can produce heat, or it's also considered that the system can do work on its surroundings, right? So either we're producing heat, right? The system, this is the, let me get back to this one here. There we go. The negative signs here, right? So the system releases heat, so we're going to have negative Q, right? So here, this Q here is negative, right? So anytime that we're producing heat, Q is a negative value. Anytime that the system does work on its surroundings, that is also some negative value. So both work, the system doing work on the surroundings or the system releasing heat to the surroundings, and we get some negative W. And we'll talk about this. This U here is what we call internal energy. So U is equal to internal energy. And most of the time we've just been giving it some capital E, right? But that's what we've been doing there. So E, energy, we're going to use this letter here. But notice here, so it's also just kind of a reminder that this change in energy, this release of heat, we're being done by the system onto the surroundings, those values are going to be negative values, right? So we have this negative Q, this negative W, and our change in energy is going to be less than 0. Right? And then just the opposite, right? If the system is absorbing heat, right, that's going to be some positive Q. If work is being done on the system, not on the surroundings, work done on the surroundings, negative value. Work done on the system, some positive value. And our internal energy is also going to be some positive value. So our change in internal energy is equal to some amount of heat plus some amount of work. So one type of work is what we consider to be pressure volume work, right? So here, this system, right, the system is pushing back on the surroundings. So let's imagine this is a balloon here, right? And we're trying to just kind of understand this pressure volume work here, because there is some resistance here. If I'm trying to fill this balloon with air, right, is that the surroundings is trying to push this in, and whatever air we're putting in here is trying to push itself out. Right? So this is just one type of work that we're considering, right? We consider pressure volume work. Right? Internal combustion engine. Right? There's 4 stages to this. Right? I'm no mechanic, but I do know the basics of it. There's 4 stages of this piston. As this piston moves down, it's considered intake. So what it's doing is, when this piston moves down, there's a vacuum in here, and it will pull a little small amount of gas in here. Right? And next stage is when it goes up, it'll compress that gas. So in here is going to be a mixture of gas and air as it comes down, and then it compresses that gas and air. And we know what happens if we decrease the volume, we increase the pressure here. So we decrease the volume, we increase the pressure. But here, when it's compressed, this little spark plug will spark, it lights this up here, and then it combusts, pushing the piston back down. And as it's combusting, right, that we have, we know combustion, we take gas, we take air, we get carbon monoxide, we get some water, we get some, carbon dioxide, water, and some energy. And that energy, right, is used to bring this back up for our exhaust. So it's pushing that CO2, it's pushing that water out of the system, and then it just kind of simply just repeats itself all over and over and over again. I think it'll show an example here, right? So here's our intake, compression, power, and then exhaust coming out here. But again, this is an exothermic reaction here. And the system, which is the gas and the oxygen, right? That's our reaction. Our combustion reaction is we're going to have some octane, gas, plus we're going to have some oxygen. We're going to produce carbon dioxide, plus some water, plus some energy, right? Some heat from that. Right? So the system is the gas and the oxygen, and the surroundings is everything outside of this container over here, everything on the outside of that. So we can see that the system is doing work on the surroundings, right? This system's doing work on the surroundings. Heat is being released to the surroundings, giving us some negative Q and some negative here. So internal energy, the system decreases, right? So we have a negative change in internal energy. So internal energy is what we consider to be a state function. So with state functions, the value of the state function only depends on the state of that system, right? And it doesn't matter how we get to the end result. The only thing that matters is where we begin, right? And I think this will just kind of explain it a little bit better. So we're talking about internal energy as a state function, right? If I'm sitting here at the base, there's two options for me to get to the top of this mountain. One, I can just take a lift, and it's just going to take me, I'm just going to stand in this lift. All I have to do is stand there, and it's going to get me to the top of that mountain. Or I can hike it. Right? I'm going to take these switchbacks, and I'm going to get to the top of that summit. Now, as far as internal energy, the amount of energy expelled either using the lift or hiking it up myself was the same amount of energy. Right? I put some manual energy here, but here, I know I'm just standing there, but work is being done. As part of the system, that lift is also part of the system. And that lift is using some kind of, using some kind of energy to get me up to the top, right? But the same amount of energy that it's using to get me to the top is the same amount of internal energy. Also, if I just kind of manually use some switchbacks here. So that's kind of what we consider to be, or understand our state function there. So enthalpy is this H here. So U is internal energy. And we should be familiar with this triangle. What does this triangle mean? Other than heat?
Change.
Change, right? So we can have some change. This is change in internal energy. And then we have enthalpy. And then this would be our change in enthalpy. Right? So enthalpy is also a state function. And then we have change of enthalpy, right? So specific substances don't have enthalpy. So I can't put this. There's no enthalpy for this. But what there is enthalpy for is there is enthalpy for reactions. Right? So this reaction will produce some change in enthalpy, but we don't have enthalpy just for specific substances here. And so we see that enthalpy is equal to the internal energy plus pressure and volume. So here, we can say that the change in energy is equal to the change of internal energy plus pressure and our change in volume. So enthalpy, so these are done in constant pressure, right? So there is no pressure change here. We do have to take it into consideration, but because it's done at constant pressure, there is not going to be any change in this reaction here, right? So if I do this reaction, we do it out in the open, right? There is no change in pressure here. But we are going to consider the change in volume. So we end up with, all right, change in enthalpy is equal to our change in internal energy plus pressure and our change in volume. Now, as far as our change in volume and our work, right? You don't have to memorize this at all, right? We're not going to be using this in any calculations, but there's just a relationship between the change in volume and work, right? And they're always going to have opposite signs, right? So here, if we have a positive change in volume, we're going to have negative work, right? If I have a negative change in volume, then work will be positive. But change in volume and work have this relationship, and they are always going to be opposite in those signs there. These are all done in constant pressure. We need to get to some calculations here. All right. So here, okay, we have some reaction, and it shows us our change in enthalpy. And what I want to focus on is the value associated with this change in enthalpy. So this change in enthalpy, when we're talking about exothermic, endothermic reactions, right, is that if this is negative here, this is internal energy, Now, if my change in internal energy is negative, is that an exothermic or endothermic reaction? Exothermic, right? It's exothermic because heat is being released by the system into the surroundings, and that our internal energy is less than zero. And enthalpy works the same way. So just by looking at the change in enthalpy, I already know that this is some exothermic reaction, right? If this was a positive value, that's going to be endothermic. Now, when looking at these two reactions here, right, I'm not going to put the amount here. I'm not going to put 0.2, let's see. I think this is actually probably a pretty good lesson here. Since we have, I'm going to write this here, so we have H2 plus 1/2 of O2, and we're going to get H2O, and this here, let me adjust this here. Our change in enthalpy here is equal to negative 286 kilojoules. Well, this is specific to this reaction, and this, even though enthalpy is a state function, this happens to be an extensive property of enthalpy. Right? Extensive means that it depends on how much we have. Right? And we can see here that we have twice the amount of moles in this reaction. So if I want to get the change of enthalpy in this reaction, again, it's an extensive property, is that, well, I'm going to need more enthalpy here. So because this is twice as much, if I want to get this enthalpy change, we're going to take the negative 200, and oh, that's a horrible left-handed 8 kilojoules, but we're going to multiply that by 2. Right? So what is 286 times 2? 572 kilojoules. And let's not forget the negative here, so negative 572 kilojoules for this reaction here. Okay? Oh, this is 520. That's why Stella's looking at me all crooked-eyed. I see you. All right, so we have 572 kilojoules for this reaction here. One more thing to note here is this is gas, this is gas, this is liquid. If I reverse this reaction, so here we're going from gas to liquid. And generally, anytime we go from gas to liquid, those are exothermic reactions. But this is now going from liquid to gas. In order for us to go to liquid to gas, if I had a beaker of water and I want to evaporate it, what do? We have to heat that up. We have to add heat to it. We have to add energy to it. Is that this now has to absorb energy, right? So here, this would be our change in enthalpy would equal a positive 286 kilojoules. So if we reverse those reactions, so it's exothermic in one direction, and if we reverse that, right, it's going to be endothermic in the opposite direction there. And we've already calculated this one here, right? We're talking about its extensive property. Is that because it's doubled, we have to double that, we get a negative 572. Now, here, Oh, this would be if we cut that in half, right? So we could also cut it in half O2, quarter of this. But if we change the number of moles there, we do have to abide by those. We're not going to be doing anything by fractions here. And then the last thing to notice here, right, is that we're going from the gas phase to the liquid phase, and we know that that is negative 286 kilojoules. But it also is possible to make a gas form of water, right? That we have some water vapor, okay? Well, the amount of energy required for that is going to be less, right? Is that we're not going to get as much heat going from gas to gas molecules as we would from gas to liquid molecules. So we can see that there's just a difference there. We won't have to be calculating those, but those values are given in the back of the textbook. So there is an appendix back there, and we need to make sure when we're looking at that, let me see if I can bring that up here. So we can see here, this is going to be, this is enthalpy, this is free energy, this is entropy. We'll talk about those in 202. We don't talk about those here. Do they have them for reactions here? Well, we can write our own reactions here, but let's talk about this, I guess, here. So here, right, even with just carbon, right? Carbon solid can be looked at as a diamond, right? Any diamonds are just solid carbon molecules, but graphite is also carbon molecules. And we can see that there's a difference in enthalpy, in free energy, in entropy here. When we look at, they give us any other ones here. What else could we look at? Give us water. Right, there's a difference between aqueous fluoride and fluoride gas, right? Is that there's different values for that. So we just have to pay attention when we're looking at those values and we're looking at enthalpy. All right. So now as far as writing some thermochemical equations. Give me a second real quick. Yeah, maybe. Just getting a little worried because I cannot find my wallet. I had it here. I came walking in. Not here, not here. Interesting. Oh, right there. I thought that was my phone. All right, all right. Whew. Now that that's over, that has to be edited from so nobody on YouTube can see that. sitting there walking around with my wallet in my pocket. All right. So thermochemical equation. So let's just maybe try and understand. Well, let's just read through this first. So when we have 0.05 moles of hydrochloric acid, so I'm going to write a reaction for this. So it says that we have some hydrochloric acid. We have 0.05 moles of this. And we're going to react it with some sodium hydroxide, which we also have 0.0500 moles of this. And it's going to form some sodium chloride. So we're going to get some sodium chloride. And we're going to get some heat. So not only sodium chloride, we're also going to get some water from this, but we're also going to get 2.9 kilojoules of heat. So write a balanced thermochemical equation for the reaction of 1 mole. We want just 1 mole of HCl. All right. So the chemical equations aren't difficult to write. I think this kind of sets us up pretty good. So for 1 mole of hydrochloric acid, we're going to use the stoichiometry here, right? So here's, we have 1 mole of this, and it wants the thermochemical equation reaction of 1 mole of this. So we know that we know that 0.0500 moles of hydrochloric acid produces 2.9 kilojoules of heat. So we can say, so for every 0.0500 moles of hydrochloric acid, we're going to get 2.9 kilojoules of heat. And this unit simply cancels out this unit. So how much heat, right, are we going to get from this, this mole here? Is that we can do this calculation. There's my calculator. So actually, yeah, go ahead and calculate this for me. What is 2.9 divided by 0.05?
58 kilojoules.
58 kilojoules. And I'm going to give you guys a minute here to look at this answer. Out of everything that we have talked about so far just this morning, is this the correct answer?
No.
What are we missing?
The change in the water.
Not necessarily the change in water, but I like your thinking, so let's just keep throwing ideas out.
Like the enthalpy that we use for the change in enthalpy for the water. Like, you know how before we did the reaction.
We did the reaction, yes.
We did the example of water.
And what was, and let's keep going with that, man. Let's see.
Water is a system, so it has enthalpy in it.
And what was that enthalpy?
Negative 286.
Negative 286.
So that's negative.
So this should also be negative. Is that this heat here, even though that it gives you 2.9 kilojoules of heat, you are responsible for determining whether that is a positive or negative value. Right? I know that this is going to be a negative value simply by it saying heat produced. As soon as heat's produced, oh, this is some negative value, this is some negative value, and this is some negative value. Right? So this is our correct answer. Negative 58 kilojoules.
So then we'll see a problem that says heat is
Absorbed.
absorbed.
Yeah, right? Heat absorbed. Correct. Yeah. Absolutely. So now, Now here we're not given the number of moles, so there is an additional step here, but it's nothing that anybody should be worried about. So here we have 1.34 grams of zinc. And in our reaction here, so it says we're going to take some zinc solid, and we're going to react that with 60 milliliters of 0.750 molar hydrochloric acid. And it's going to produce 3.14 kilojoules of heat. And let's get the rest of this here. So we are going to produce some zinc chloride plus some hydrogen gas. Right? Does anybody recall what type of reaction this is? It's going to be on the exam. Just saying. What type of reaction is this? Decomposition, combination, single replacement, double replacement, A, B, C, right? This is double replacement. We'd have for this, we'd have something like AB plus C, CD. This is just A plus CB. So this is a single replacement reaction here. Is that the chloride is going to go with the zinc, and then the hydrogen is just left over. Right. But back to our problem over here. Plus we're going to get 3.14 kilojoules of heat. Now this value here, since it's produced, let's just jump ahead, and it's going to be a negative 3.14 kilojoules of heat. Determine the enthalpy change per mole of zinc reacting. Well, we know we have 1.34 grams of zinc, and we need to get to moles of zinc. So periodic table says 65.41. So we have 65.41 grams of zinc for every mole of zinc. So those units can go away. Now it's just like our other problem, right? We have moles of zinc. I know how much the reaction is going to produce here. So we're going to put 3.14 kilojoules. Nope, I think I've already, nope. I jumped the gun here, Let's calculate this first. What is this value here? So what is 1.34 times 65.41? Like this?
Mm-hmm.
All right. So this is going to be moles of zinc. So this value here, when we write our thermochemical equation, right, we're going to have, for every 1 mole of zinc, we're going to have 0.0205 moles of zinc here. So so now we can go ahead and do this over here. And what is our answer here?
Negative 153.2.
So negative 153.2 kilojoules. So that would be our enthalpy change there. So our reaction is we're going to take iron, plus we're going to take some chlorine, and we're just going to simply get FeCl2. Plus 8.6, so plus. All right, so our limiting reagent, let's start there. So we're going to have 1.80 grams of chlorine, and we have 1.42 grams of iron. Our limiting reagent first. So this is 35.45 grams per mole. Iron is 55.85. 55.85 grams per mole. Grams cancels out, grams cancels out. So how many moles of chloride are we going to have here? 0.0508 moles of chloride. And how many moles of iron are we going to get? 0.0254 moles of iron. So now we have to decide which one's our limiting reagent. So here, everything here is a 1-to-1 ratio. So if we're going to produce this iron here, or this iron chloride here, for every 1 mole of chloride, we're going to get 1 mole for every 1 mole of iron, we're going to get 1 mole. And we can easily see 5.08 times 0.0254. So the limiting reactant here is going to be the iron. So now that we have our limiting reagent, this is going to be 0.0254 moles of iron as our limiting reagent. Right? Everything looks good. All right. So now we're going to, right, we know what, how many kilojoules we have here. We're going to use our, so we have negative 8.6 kilojoules over 0.0254 moles of iron. And this is going to give us something in kilojoules per mole. So what is 8.6 divided by 0.0254? Negative 338.6. So we'll make it 339. So negative 339 kilojoules per mole of iron. Well,
Wait, is that 8.6 or 0.8?
8.6.
Oh, so that's, I thought it was not behind the 8.
So
Yeah, there we go.
what is our value then?
Yeah, 330.
330. Okay, so negative 339 kilojoules per mole of iron. Well, this is a 1-to-1 ratio, right? It is a 1-to-1 ratio. So here, we can just do this math here. We're going to multiply it by, let's see, so there's going to be 1 mole. Using 1 mole of iron, we're going to get some amount in kilojoules, which is equal to negative 339 kilojoules. All right. Enthalpy changes standard state. So something we're going to also notice, this is going to come into play just at the end of this chapter here, and then going into 202. So we've talked about standard temperature and pressure, right? Standard temperature, 1 atmosphere, so STP, right? Standard temperature, pressure. Standard temperature, 25 degrees Celsius, and 1 atmosphere. So how we signify that, that something happens in standard conditions or its standard state, is we simply signify it by this here. So if we're asking for the change in enthalpy, so our change in enthalpy, as long as we see that little, and where they, no, I think I have it placed in just the opposite value. Here, whether we see it here, whether we see it, this is free energy, this is going to be, this is entropy, we can do it for internal energy, right? As long as we see this little mark here, this represents that it's going to be done at standard temperature pressure. So if it's not provided to you in the problem, I don't know what the pressure is, I don't know what the temperature is. No, we do know. We know that it's 25 degrees Celsius, which is 293.15 Kelvin. Right? And we know the temperature or the pressure is going to be simply just 1 atmosphere. So anytime we see those conditions there. So standard heat of combustion. So let's take a look at it, and here it is, our standard, right? This is done in standard conditions, standard temperature and pressure. So ethanol combusts at negative 1366.8 kilojoules per mole. The amount of heat produced when 1 mole of ethanol undergoes combustion at 25 C at 1 atmosphere yields this value here. Looks off a little bit. What's going on there? There we go. That's why it looked a little odd. All right. So because this is done at 1 atmosphere here when we combust this, right, is that we just designate it with that little symbol there. So, right, here we see a bunch of different ones, but also noted, right, we know that's that little sub C here. You're going to also start to recognize these little values here. Like this is going to say sub C. We could say, I think I might have used this, right? So this is vaporization, right? So these little things, this little C would just mean combustion. This is going to be vaporization. We might see one that says, right, this F here, this would be like formation is what it's considering here. So we just have to have those little marks there. But over here, this is all the enthalpy of combustion, and we can see that it's done. These are done in standard conditions, and we see that there are kilojoules at 25 degrees Celsius. And if we reverse those reactions, what happens to these values? Right, they also go out. They'll all be changed in opposite directions once we do that. If we increase the number of moles in any of them, because this is enthalpy, because it's an extensive property, is we also need to, if we double it, we double those amounts. If we triple them, then we triple those amounts. So let's see what it's talking about. These are probably one of the last couple of problems that I think I have here. The combustion of gasoline is an exothermic process. Determine the approximate amount of heat produced by burning 1 liter of gasoline, assuming the enthalpy of combustion of gas is the same of isooctane, and they give us some values here. So I'm going to just walk through this reaction here. Right? Is that in order to determine this, they gave us some amount here. They gave us 1.00 liters of octane, right? In all the calculations that we've been doing for these thermochemical equations, we need the number of moles, right? So what we're going to do here is, because they gave us the liters here, we're going to use the density. This is the density of isooctane. We're going to convert the liters into milliliters. We use the density here in order to convert those liters now into some grams. And then we're going to use the molar mass of it in order to determine how many kilojoules we're going to get, right? Because for every 1 mole, right, this is telling us here, it's negative 54.60. So if I rewrite that, it's negative 5460, and it says kilojoules per mole. So if we can convert this 1 liter of isooctane into simply just moles, and we know that this is per mole, we can calculate what that change is here. So we end up with negative 3.31 times 10 to the 4 kilojoules. So let's work at another one here. So that was just kind of the walkthrough, but this is our actual calculation now that we're going to be doing. And we're starting with 125 grams of acetylene. For the exam, I'm not going to make you come up with these formulas. We don't know yet what this is. This is organic chemistry, but acetylene is C2H2. Okay. So we have 2 carbons, so 2 times 12.01, and then we have 2 times 1.01, 24.02, 2.02, 26.04 grams per mole. All right, so we know what the molar mass of this. If I have 125 grams of this, 125, then we're going to put 26.04 grams of acetylene for every mole of acetylene. We didn't need to use density here because we weren't given volume, so density was not required. But we do need to know right? So here's acetylene. It's negative 1,301 kilojoules per mole. So it is negative 1,301 kilojoules per mole of acetylene. So we can determine just how much enthalpy that is. So what is our final value over here? This is 1301. So 1,301. 1,301. So how much? What is it?
6,245.
Is that what we got? Does that seem to match everybody? We're good?
I used the 4.7619,047, the continuation of my calculator, and I just put times negative 1,301, and I got negative 6,195.
So 125 divided by 26.04 times a negative 1,301. I get 6,245.19963. So it might be maybe some couple numbers mixed up. Yeah, so I do get this as a match. All right. Just in time for Hess's law, so I think we're going to just finish out the rest of this chapter. You will see Hess's law. You will see some of these equations that we've gone over here today on the exam. Hess's law is definitely going to be on the exam. And as long as we understand one thing with Hess's law, right? So Hess's law, right? The amount of heat has to be calculated using Hess's law. there's two ways to get the amount of heat involved in these chemical reactions here. Right? One is we have to measure it experimentally. Right? So we do some experiment, we can measure that amount of heat. And the other way is to calculate it from somebody else who's already done all of that stuff. Right? Is that here, right, we see a bunch of reactions over here. We also see this table over here. You don't see it, but I see it on my laptop. All right. Is that we can use this here. So notice how this is enthalpy of formation, right? So enthalpy of formation. So how much enthalpy in order to form these products, all right? So what we can do is let's take a look of this enthalpy of formation here. Right? So the enthalpy of formation here, right, is how much enthalpy here in order to produce this CO2 gas. And it's going to take a negative 335 kilojoules. And when we look at Hess's law can be written as some sum of enthalpies. Right? If we take the reactions, we take the enthalpies of the products, if we take the enthalpies of the reactants, what we can do here is this is what we're going to be doing here. This is what we need to know. We do similar stuff in 202 coming up next semester, but the enthalpy of the reaction. Right? What we're given, that table that I showed you that had all the enthalpies of formations, right, is that that's the enthalpy of formation of the products, right, the enthalpy of formation of the reactants to get the enthalpy of the reaction. So what this means here, we're going to see some stuff here. So this means the number of moles of it, right? That's what its N stands for. N stands for the number of moles. So we can know the number of moles simply just from the reaction. The reaction is going to give us the chemical formula of the reaction is going to give us the number of moles. And we multiply that because, again, enthalpy is an extensive property, so we have to multiply that by the number of moles. So as an example, right, and we know what this squiggly sign means here, right, this little E right here, this means sum, right? So on your Excel spreadsheets, right, that just means sum. So if we take a look at this reaction up here, this reaction says for every 3 moles of nitrogen dioxide plus some water, we're going to get some nitric acid plus some nitrogen monoxide, and we want to know the enthalpy change for this. So now we see a bunch of these values here. These values here, let's take a look at one of them here. Let's take a look at 2 of them. So nitric acid. Notice, right, aqueous, gas, liquid, we have to know, so the chemical reaction will tell you which one you need. So we're looking at aqueous, and this is where we get that information, negative 207.4. So going back to our problem over here, we can see that's where this value came from, negative 207.4. And the 2 moles over here came from the reaction. There it is. It's 2 moles there, and because enthalpy is an extensive property, well, we now need to double that and include that in here. So we're going to add the products. It's always products minus the reactants. I'm going to rewrite this real quick. I think I have time for this. Maybe, maybe not. We'll see. So as far as products minus reactants, right? So we need to have these brackets. So our products are nitric acid and some nitrogen monoxide here. And I think that might show it clear here. So these are our products, and then they're bracketed minus the reactants. Our reactants are, right, nitrous oxide, and then we have some water here. And then we sum all that up, and for the reaction now, this is our enthalpy for that reaction. So let's work through one. I think we have time for one here, one or two. I'm hoping we can get through both of these here. Here's our reaction for a diamond. So I already pulled the enthalpy of formations off for us. Right? So if we're talking about graphite turning into a diamond, right? Graphite turning into a diamond. Just how much, what enthalpy are we going to need for that? So again, it's products minus the reactants, right? Products minus the reactants. So the change in enthalpy, I'm just going to put Rx in here for reaction, is the products minus the reactants. Well, in the reaction, we can see that what's the mole ratio of graphite? 1. It's a 1-to-1 ratio. We can see those there. So what we have to do is products. Our product is diamond, so we're going to have 2 kilojoules per mole, right? Minus the number of moles. I'm sorry, we do need the number of moles here. So it's going to be 1 mole divided by, that's a horrible slash, divided by, oh no, not divided by, times, this is getting sloppy. So these units cancel out, right? Mole cancels out mole, so we're going to get kilojoules. So this is our product minus the reactant. We have 1 mole of graphite times 0 kilojoules per mole. Moles cancel out. What is 1 times 0? That's 0. This is going to, 1 times 2 is 2. So this is going to be 2 kilojoules. All right? But always remember, it's products minus reactants. Products minus reactants. We're going to learn about free energy in the spring. Products minus reactants. Entropy. Products minus reactants. Right? When we're doing temperature change, final minus initial. Right? Final, our product, minus initial, which is our reactants. So let's do one more. We have time for one more real quick. Here we do have some coefficients to worry about, but we're going to do our products first. So our products are going to be CO2. So we have CO2. Do they give us carbon dioxide, negative 393.5? So how many moles of that? So there's 1 mole times negative 393.5 kilojoules per mole. And I'm going to add that, because this is the sum of this. We're adding these together. The other one is water, and water is negative 285.8. And there's 2 moles of that, plus 2 times a negative 285.8 kilojoules per mole. And we're going to subtract products minus the reactants. And I'm going to write our reactants down here. One of the reactants is methane, so negative. So we're going to have 2 of those. Nope, just 1 of those. So 1 mole times a negative 74.60 plus 2 moles times 0 kilojoules. Right. So for O2, and let's just verify, make sure I didn't forget to write that, but if we look at oxygen, there it is, O2 gas, and we can clearly see that it's just 0. So I already know that this here is just going to be 0. This is going to be negative 74.60. So what is our answer to this? So what is, this is 1, this is 2, so we're going to have, let's see if we can calculate that. I'll try and calculate this with you real quick. So we're going to have a negative 393.5 plus 2 times negative 285 0.8. I put brackets here, so please use brackets, minus a negative 74.6. And what did we all get?
2,000.
Negative 806.
Negative 393.5 plus 2 times negative 285.8. I got negative 890. Anybody get this? Negative 890? All right. So we really just kind of need to be cautious with those brackets. If you're having trouble calculating this last one, stick around and I will help you make sure that we understand how to calculate that. But I think that brings us to the end here, and we are done with chapter 9. All right. All right, I have some good stuff for you tomorrow. Get you all prepared for the exam. If you have any questions, stick around. If not, we will see you tomorrow.